So currently I work as a head of software architecture in a startup called Takeoff Technologies. We're doing grocery delivery, a startup in the United States, in Boston. Before that, I worked as CTO of Zakaz UA. It's the biggest grocery delivery company in Ukraine. We actually built this market in Ukraine. So, it appears that this business is exceptionally hard in terms of engineering, number of components, and so on. Before that, I worked for Upwork, and that's it. Also, I organize a lot of conferences in Ukraine, and also co-organizer of this conference. So, what about my work? Currently, we are building the grocery delivery usually thing, but with additional component, which we call MFC, Micro Fulfillment Center, and this robotic warehouse. So it's sounds cool. About my talk. So basically, what is Groupware Systems and distributed systems, and what's the difference? I think current modern term of this type of systems is collaborative systems, where users involved into editing something together in same time or separately in different time zones and so on. But eventually, the result of their collective work, collaborative work, goes into one single entity. Other examples of this type of systems is peer-to-peer systems, different like BitTorrent, WebRTC, and distributed algorithms, and so on. And I think that most of you using this type of approaches with nodes, calendars, contacts, synchronization between your devices. So and messengers, obviously. Is the reality we are facing right now. All application goes to cloud, and in cloud there's a whole bunch of interesting problems which are solved partially with different algorithms, so different approaches. So what distributed setting for this particular talk? I assume that we have some users have devices. Devices must be synced, and users can work on something together. For example, Google Docs, when you editing it with two and more colleagues, so I don't know. Also the new hot thing is offline mode, when you can start work on something offline, and eventually it will converge into your something. And it will be useful, and eventually it's possible to start work offline. Why I'm talking about that on Python conference? First of all, I think that Python is mostly popular in two major areas. The first one is web development, so for backend developers, and the second one is data science. I don't know much about data science, so I'm speaking as backend developer in Python. And I'm interested, by the way, I'm curious, who is backend developer here? Okay, at least half of. Other half? No, okay. And another hot thing is P2P systems, but I don't think I can cover it right now because it's too hidden for me right now. And here is a figure which represents the role of Python code in distributed setting. So by client, I mean browser or device or anything which using your Python API or Python communication channels, for example, WebSocket, I don't know, it doesn't matter, but the idea is that Python plays crucial role in this part, and therefore we should at least understand how it works, how distributed settings, distributed algorithms works, and how synchronization between devices works. So is it clear from figure what Python does? Okay. And I would like to start with consistency, with data consistency. So there is a couple models, and the most famous one, I think, for those of you who are working with databases, the strong consistency is most obvious, and I will not talk about isolation level for transactions, but the idea of strong consistency is that you have serializability of your operations, and in any point of time you can do only one operation. Read, write, it's not matter, but the idea is that only one, and the single point of failure is the queue, which maintains this serializability. So there is, like in 80s, I think, I believe there was some jump from single machine to multiple machines, and the two-phase commit was invented in 82, and it was a cool thing I think for that time, because everything was slow. But nowadays the performance is not good, even in with some Quorum-commit setting, where you have multiple machines to get quorum and so on, and actually it's add latency to your requests, reduce obviously throughput, and I will not talk much about that in this talk. But the cool thing about that there is no conflicts, right? So you don't need to think about conflict resolutions. Another type of consistency is like spectrum, and it's another end of spectrum is weak consistency. When you write, you will get no guarantees that it was written. And there's a nice hack about that concept is redo writes, when you can, client which write can read own writes, but all other sites or other participants of a distributed system is not guaranteed that they will receive this write. So we can pretend that it is written. And more fresh thing called eventual consistency. I think this term invented by CTO of Amazon, Werner Vogels, and the idea that participants, all replicas, will receive states, will receive all updates eventually, and achieve same state when all updates was delivered to correct replicas. And this type of consistency must have two major properties. The one is convergence, I already told about that, and the second one is termination, that when we're receiving and applying updates, this operation can be terminated. And famous thing about this famous databases which employs this model, Ryak, Mongo, Cassandra, CouchDB. I think CouchDB was the first one open source, and after that Mongo and others was introduced. And the subset of eventual consistency called strong eventual consistency, and there's additional guarantee is the same properties of eventual consistency, but also additional guarantee which says that if we receive all replicas, all updates from all replicas, the states between all replicas will be equivalent. And it called, like in this CRDT communities, it called COM, consistency as logical monotonicity. So it's like kind of joke that it called AC 2.0, associative, commutative, idempotent, and distributed. The first one, you know, kind of different. So I would like to start with 3 basic concurrency problems which facing when we start to do something in distributed setting. The first one is divergence. It's like 2 users editing the same document in different places, and eventually they should merge these changes into one document. The second one is causality violation, when you do sequence of operations, the user A and user B, and there's difference between this orders of these operations for different users. So if user A sends a message, sends its operations to user B and vice versa, the operations will be in different order. And the last one is intention violation, when we preserve the order of operations, but the result is not what we intended to have. For example, if you draw in like two SVG or one SVG document, we edit in one SVG document, and one person draw in circle, another one square, and when it merged, we get in square over circle. Obviously, the result is not what intended by first and second user. And as engineers, obviously, the idea is that we want to avoid these issues and to think like, can we log something, or can we do transactions, or can we delay transactions and then we can roll back transactions, or add inversions. And eventually, all these approaches much more complex than approach of conflict-free replicated data type. Because to implement it correctly and to verify that it works correctly, you should spend a lot of time. The solution of I think most issues of a distributed system so far is conflict-free replicated data type. The distributed settings in network exist in network, so you should understand that networks have limitations, and somehow we should cope with that limitations. First of all, the packets can be delayed. The second one, there may be loss of packets. The packets can be delivered in different order, out of order delivery. Packets can be retransmitted, that messages in our system can be retransmitted. So we should cope with that errors, because if we apply just everything we receiving or not receiving, we will get different states for different participants of the system. So in 2011, a guy called Mark Shapiro and others in RIA Institute in France employed the semi-lattice algebraic structure to solve the problems with distributed setting and to support causal order of operations. So in order to cope with network errors and support partial order of operations, we should support 3 properties of our messages. The first one is commutativity, so the order of operations does not matter. The second one, associativities. If we have 3 operations, it's not matter in which order we apply it. And the last one is idempotency. So if we receiving 1 or more operation, it not matter because we applying it only once to our state. The interesting thing about Shapiro that is the guy who invented proxy servers. So quite famous, I should say. And these properties provide us ability to be strong eventual consistent. So our state will be eventual consistent because it follows from definition of eventual consistency. So let's try some trick with plus operator. So is it associative? Looks like yes. Also commutative, but it's not independent, right? So we can't use plus. It's not what we want. But if we replace operator with union, is the whole new idea. Okay? So looks like union works for us, and state will converge on every replica. And I would like to explain it in plain Python instead of formulas. So let's assume this is our list of messages, and the tag is technically it's vector clock for message. Do you know what this vector clock is? Okay, one guy know. So the point is that every replica, the participant of the system, keep tracking of number of operations for themselves. So like for site 1, there is 1, 2, 3 sequential order of operations. And for every site, there is different different order of operations. So we have 2 sites, site 1, site 2, and operations 0, 1, and 2. And you can see duplicates, and you can see concurrent operations when they have the same tag and they're concurrent. So it looks like we should resolve conflict which will appear. So how we can support this idempotency property? It's easy. We can group by tag and site, and we easily get rid of duplicates. And how we support partial order? We sorting by tag and afterwards site. One of approaches of support partition order is to sort in lexicographical order after number of operations, because operation can be concurrent, but afterwards we should achieve the same state on all participants of the system. Is it clear? Yes? No? Okay. Cool. Here is the figure which represents the difference. First of all, there is blue box which represents what guarantee CRDT provides to us. Else is not related to CRDT. So transport you should maintain by yourself. I will provide some ideas, but it's not related to this talk. And conflict resolutions, there is some type of CRDTs it's already implemented. They provide kind of mechanism to resolve conflicts. And also it's possible to implement that yourself, and the resolution depends on domain. You should try to apply this concept. And obviously there's application access API, which access to data with resolved conflicts. So some ideas about transport. I think that there's only 2 ways to support it in browser. You can either use PubSub and employ some kind of protocol which provides guarantees of delivery, kind of stomp, I don't know, or do it by yourself. And another approach is to use server-sent events. SSE is fresh concept. Who heard about event stream? Okay, one guy. So it's the list of events. So you connect into web server, you receive a list of events, and in case with all events, you receive the offset of this event. And if you need to, if connection was dropped, you reconnect and specify on this offset and receiving all events after that offset. So it's kind of long poll, but in more modern way. And WebSockets to send replicas to other parts of the system. So let's start with simplest data type, CRDT data type called G-counter, growth only counter. So here is described the interface. the method called constructor. I forgot to rename to init, sorry, because I translated it for another language. So the idea is that we can do only one thing with counter. We can two things. The one is increment counter, and the second one is to get value of counter, and nothing more. And we need merge to merge updates for all sites within our system. Here is sample example of payload of this counter argument of constructor. So kind of we have on key is the number of site or participants, and value is the value of counter for this particular participant. Here example implementation in Python. Here is init correctly replaced. So I'm init counter with my site ID, and the whole idea is in in this max function. So when I get in all replicas from all sites, I just apply the replica max value between my value, which is value in my state, and value in replica I received. So it's basically the easiest conflict resolution algo for CRDT. Here's example function, the test function. So the idea is that here is, oh, this is wrong. This is for, okay. Then let's go to this one. This is PN counter, the same idea, but positive negative means I can increment and decrement. And here's the same idea as in previous counter, but I'm keeping two counters, for one for growing values and one for increment, the second one for decrement, and that's it. And when I query it, I just get in sum of these values. And oh, this doesn't work. And here's an example for PN counter. So I increment twice and decrement once, and so on. And output for that is here. So I have 0, my initial state, increment twice, all other 0. Decrement once, and here is my state after merge. And this is for concurrent operation. So here's my initial state, 1, converge, and so on. And it not looks obvious, this example, in terms of text output, so I realized it too late. And I draw the figure, but for others. So the next data type called MV register, and it register of values which can support without data loss. The register without data loss. So every input which set by any replica will not be lost ever. You should explicitly redefine it. So it's kind of manual conflict resolution. So the idea is very simple, right? We can set value, it's for particular site ID, and here we can update value for everyone except myself. And here's example function, test function. So I'm setting V1 for first additional and V3 for third, and eventually I should get merge state. And it looks like that. So we are setting for this, and here is merged value. And this is schema of the figure of how it works. So I set here is concurrent operations. And when I get replica from S1, I got V1 and V3, and I have not get replica for S2, so S2 visible only V1 value. Eventually, the value will be the same as here. So this looks pretty useless. I should say, these basic data types. And you can't build much with that. But in August 2017, the new article came out called JSON replicated data type, and I think that's it. The idea is that you can build the distributed JSON data type, and in case any of, for example, it's a very good example. So we have initial state, we set key, or get key, and we get, like here is replication, and we get both key presented in our JSON. So the data type is completely distributed. And here's example of conflicting operations. So we have, here we trying to set for same key different kind of types, different types of data. Here is object and here is array list. And we will get eventually markers that we should resolve somehow this conflict. And conflict resolution of any data type depends on domain very much. So in practice, here's our implementation of shopping cart using CRDT. This is kind of, there's too much code, so I tried to reduce it to most valuable part for you as audience. So here's, we're using Redis as a storage for this card, and here's the method which add in new record, new operation of something with card. And here's like vector clock, device ID means on which device this operation was executed. Checksum is for lexicographical order, and payload means the command, for example, +1, -1, add product, remove product, and so on. This is represented as commands within the system, and we are using just dumping this payload into Redis. So the basically what we implemented was command-based or op-based commutative replicated data type. There's two types. The difference difference is like that. So in one type you represent every operation in your system as command, and you keep history of commands and building state when you query your state building from commands. And other is state-based convergent replicated data type. It apply your updates right after delivery, and on query you just gathering state. So you don't need to keep this history of base of operations. The difference is like that. This is where the op-based types is very easy to implement. It's very very simple mental model, and you can always fix bug and rebuild, and it will work like you expected. And the state-based is very different because updates already updated, and you can't rebuild everything from scratch. So what other types of which exist in CRDT? So I mentioned register, multi-value, but there is another one is LWW, left right pins, counter, gset, sets. Eventually they like invented 2p set. You can remove elements, it's a cool thing. And other optimizations like or set, you can tagging every element you can add or remove multiple times. And there's multiple algorithms which mostly developed for collaborative editing, text editing. So they very specific in that way. And also I mentioned JSON data type, which is not listed here, but it exists, it's very cool. And what tool we have? In Python, it was surprisingly for me that there is not much done in this area. I found only 3 semi-alive libraries, kind of, which I think that students trying to implement something and they just abandoned after it was initially implemented. But in other languages, and especially in databases, there's a lot of movement around that. The first one, production database, was developed by SoundCloud called Roshi, and they developed the cluster, the very specific CRDT type for their business. After I think the first one after Roshi was Ryak, who implemented CRDTs and who I think never mind. So I just the bad word in my mind about this, because they implemented it twice. The first one is because of amount of information. The storage was fucked up. I found that, and they re-implemented it with sharding of CRDT files in order to be stable with these data types, because there can be huge data sets. You can download like 3 gigabytes of counters easily. So it's not, I think it's not funny for user. And Redis Labs testing CRDTs right now in beta. So probably we will see CRDT soon in Redis. From other worlds, JavaScript communities working, I think, pretty much on that. The most alive, I think, is GAN framework. They update it daily. It's really huge. There is P2P support, encrypted, end-to-end encryption, and WebSockets, and everything which is possible to implement. They already implemented. They have cool website, and I think that eventually we should integrate with some of them. The other one is YJS, approximately the same. It's more framework to build new CRDT types, not end-to-end product like GAN framework. And these two semi-alive, I don't think we should discuss it. Because CRDT is so simple, it's so easy to implement new types. But I think with this comes responsibility to implement it correctly, because it's easy to to make too much traffic on your website, or too much data set, too much payloads of state to your clients. So for us, the card is easy example, because there is cutoff time when you make order and there is no card anymore. So we just did a very easy calculation is how many products people buy and how much times they add and remove it from the card. So we have this information. It was easy to build. And other thing is it's hard to verify that what you have implemented is correct. So you need to employ some prover like TLA plus or something like that in order to verify that it actually works. Here is a list of sites which using it in production. The most famous is TomTom and Facebook. I think that's it. Any questions?
Please.
No questions. Everything's so clear. Cool.
Are you already using something like this in production?
Semi-production. A closed beta of our new product. We're building whole new product, so we're using it for shopping cart, and currently we are building billing system to manage assets and to manage money flows.
Do I understand correctly that your current project, your current startup, is not in production phase already?
We have platform 1.0 in production, and we building platform 2.0 with micro-fulfillment center with robotic warehouse. So a lot of work.
Okay, so I think that this distributed stuff is rather, so to say, complex to get initially. Maybe somebody will ask you in person with more specific things. Yes.
Hopefully.
Thank you very much.
Thank you very much.
Thanks. Let's speaker again.